Well, thank you for this opportunity. This is work that I've been doing for 40 years, believe it or not. Quantum mechanics is about 100 years old now. It's about this time, 100 years ago, Schrodinger came up with his equation. So about half the time we've had quantum mechanics, I've been working on this problem. And it has to do with quantum spin magnetometry for ultracold neutron electric dipole moment experiments. Now, we heard about axions in regard to dark matter, but if you look at a neutron, whenever we have a picture of a nucleon with quarks in it, we always like to have this little triangle. Well, that's impossible because if you had that, you'd have an electric dipole moment. So on average, these quarks have to be basically in a line. I learned this in a theory talk last semester. Sometimes you go to these theory talks, someone like me can actually learn something. And this was a eureka moment for me. If you have a look at the QCD Lagrangian, you actually put in some angle and introduce CP violation, which induces an electric dipole moment. This angle, this measure would be less than 10 to the minus 10. And you say, okay, so what? Let's set it to 0. Well, if you try to do that, you get a divergence, and it's something like a logarithm of the 11th order. You interpretively put this into, a standard model of electroweak interactions. So this is sort of an interesting mystery. So the neutron electric dipole moment has been in this for a long time. Next slide, please. So there's a new electric dipole moment of a neutron experiment being set up at Los Alamos. This is the used to be the Los Alamos Meson physics facility. Yale had a big footprint there with particularly the Vernon Hughes and the G-2 of the muon. And anyway, this accelerator's about half a mile long. It looks shorter on this picture, but this is a view out of my dining room window at home was over the same area. That's Rio Grande Valley. This is the accelerator. And this is ultracold neutrons. So neutrons so slow, about 5 meters per second, you can store material bodies to reflect from the walls. And we developed the world's most powerful ultracold neutron source that runs on this accelerator that's located at the end. And it's not the highest energy, but you can put a megawatt of power on a target. I think that's higher than any that's existing. Maybe the SNS is higher. But anyway, next slide, please. So this is a picture of the source. There's no scale here, but this is a guardrail. So you don't walk off. It's a little bit like a Mayan step pyramid. The famous theoretical physicist actually fell off the step pyramid and was tragically killed. Even done one of the inventors of the Z transform. Anyway, so there's a little guardrail so we don't want to go off absentmindedly. That gives you a scale of the experiment. This is going to be the new ultracold neutron experiment. And these are some other experiments that were done there. We built this, designed all that, the source around 2000, and there's been an upgrade. The first author on this paper is Doug Wong, who actually was an undergraduate at Yale. He worked in my lab. He went on to do great things. I think he's in Austria now working with the ultracold atom group there. So the idea is we have ultracold neutrons, we can feed an experiment, and basically it's a resonance chamber. You can detect neutrons, ultracold neutrons with perfectly 100% efficiency. They're perfect quantum particle. They bounce off walls, just like a quantum mechanical barrier. There's no electrostatic interaction. There's a nuclear force, but its wavelength of the neutron, ultracold neutrons, 100 angstroms, and much, much bigger than the space of the atom. So it's a perfect external reflection from most materials. You can store them in a bottle, polarize them, detect them. And one problem with this is you look for electric dipole of the neutron, this precession experiment, and the level of sensitivity now is less than a nanohertz. So you have to monitor the magnetic field. That's been done with what we call the mercury co-magnetometer. And this was, this is an experiment done at PSI. This was published in 2020. This new experiment is being built now at Los Alamos. So they called me up and asked me to talk about the co-magnetometer and how the spin lifetime improved. Next slide, please. So I started looking at this, and I actually only completed this work last week. And it's one of the most interesting things I've ever worked on. But it took 40 years to get to this point. I wrote a paper, and I just sent this. And I sent to Academia Quantum. The advantage of sending it there is I'm the chief editor, so to answer Keith's laments over scalding referee reports and rejection of new ideas, I'd say, I'm going to do this. And people send me stuff that's a little bit off the wall. We're going to publish it. Now, if you send a paper proving with high school algebra that Einstein's theory of relativity is incorrect, it's probably not going to get published. But I put this out as an advertisement, and if you want more about it, the journal, I'll tell you about it. It's an open access journal. It's a model that I strongly support. I don't like anything, but I hate more than anything else trying to read a scientific paper that was done on public funds. You can access the information. So I'm a big supporter of open access publishing. So anyway, what I did was there was conflicting data over the last, maybe 15, 20 years about how the relaxation of the atoms occurred. You put a magnetic field on, you can slow it down, and you can measure the correlation time versus the sticking times on the walls of the cell. And while I was teaching quantum mechanics this last year, by the way, it finally occurred to me how to do this problem. And you can use the work out the van der Waals attraction of the atom with the wall. You only need to know the dielectric function of the wall material and the spectroscopic data for the atom, SF values and their frequencies. You work out with the van der Waals forces. And if you do that, for mercury infused silica, you found out that there's about 70 bound states at the surface of the fused silica. And it's the most deeply bound level is 0.21 electron volts. That's a lot. It's a lot higher energy than 25 millielectron volts for thermal atoms. And putting this all together, you have these hundreds of states, nearly 100 states. Mercury atom or xenon 129 applies to that too. Gets in there and it really has a hard time finding its way out of this forest of the functions. And it shows well on this. Each one of these dots is the curved line is the WKB approximation of the energy levels. The other one just a fit to a logarithm of energy. So final slide. And the other thing is the effects of hydrogen. This work I did back at the University of Washington in 1991. Emboldened by all this, I finally went through and analyzed all the data. And it turns out that hydrogen gets on the walls. Atomic hydrogen is very reactive. It tears apart bonds. And those leftover magnetic moments associated with the torn apart bond causes relaxation due to paramagnetism. And I just demonstrated back then that if you rinse the cell with oxygen, it would come back. This was successfully applied at the PSI experiment. And the big thing I learned, I mean, tell the people, those animals, your vacuum has to be excellent. Excess hydrogen control or eliminated. This was also true for the hydrogen maser. And it turns out atomic hydrogen will break down Teflon even. So, and I think that's it. Thank you for your attention.